Hi, I'm Tony from Mirus, and I'll be taking you through this next tutorial in our SOLV computer simulation software series, using SOLV for complex harmonic studies. This tutorial assumes that the user has a basic understanding of how to use SOLV. If that isn't the case, I'd recommend that you take the time to view previous tutorials in the series that will introduce you to SOLV and walk you through some of its features. Due to the potentially serious nature of issues that power system harmonics can have on sensitive equipment, many consultants, building managers, industrial facilities engineers are now requiring pre-construction harmonic analysis reports for their projects. For many, this would require the use of expensive power analysis software and can be quite time-consuming. But when equipped with the relevant source and load information, accurate and reliable harmonic analysis can be performed using Mirus's free SOLV simulation software. With SOLV, you can simulate either the utility supply or generator supply or any such source. You can combine all the linear loads, and they can be combined arithmetically into one linear load branch. There are 9 nonlinear load branches, and when necessary, you can combine these similar nonlinear loads and expand the loading capability. SOLV is uniquely equipped with the ability to enter background voltage distortion and voltage imbalance to better simulate actual conditions. And transformers can be entered on each load branch to accommodate more complex one lines. In this analysis, I will use a hospital application where the contract documents required an harmonics analysis report to confirm that various mechanical HVAC equipment at the site would comply with IEEE standard 519/2014 requirements. A summary of the HVAC equipment load was prepared from the equipment specs provided by the mechanical contractor. The nonlinear load HVAC equipment included 3 400 horsepower active front-end chillers, and when we factored in redundancy, the loading of these chillers could be modeled as 75% maximum. There were chilled water and other pumps, 105 horsepower, of which were again active front-end variable speed drives. Those were for the 30 horsepower and larger. There was 95 horsepower of 6-pulse VFDs, which had 5% DC chokes. Those were for the 25 horsepower and smaller. And there was 107.5 horsepower total of 6-pulse VFDs that had 3% AC line reactors. The AFI VFDs were modeled as 18-pulse loads, since SOLV doesn't have AFI models. And at low frequencies, the harmonics are similar. But AFI equipment can introduce high-frequency harmonics, which were not simulated. Other loads included a total of 665 horsepower of air handling units, which were equipped with highly efficient EC fans. The larger of these units had Mirus lineator harmonic filters that totaled about 600 horsepower. The smaller units, there was no additional harmonic mitigation equipment added, and that was about 65 horsepower. There were 4 15 horsepower cooling tower fans. They were 6-pulse VFDs equipped with 5% DC chokes. There was 44.5 horsepower of total miscellaneous fan loads. They were 6-pulse VFDs equipped with 5% DC chokes as well. The linear load component was combined. It had multiple fixed speed motors totaling about 146 horsepower, and we used a 0.9 power factor. The electrical one line with the utility supply is shown here. There were two 2500 kVA, 13.8 kV to 480 volt transformers with about 5.75% impedance sharing the load on two buses. Our request on the utility easily yielded the necessary fault level data of the electrical supply, which was 13.1 kA at 13.8 kV. Being a critical hospital facility, the site was equipped with backup generator capacity that could carry the entire load if necessary. This included two 2000 kilowatt 480 volt generators with a power factor of 0.8 and subtransient reactance of 13%. Armed with this information, let's now move to the SOLV program and set up the simulations. So let's start our SOLV simulation with a new SOLV file. So I've opened up SOLV and I've selected a new file. This shows, our source, where we can enter our source information, our utility, transformer and generator information, cables, power factor, correction capacitors, user transformers, our loading information. Our linear load is the first branch, and we have 9 nonlinear load branches. We can put a description of our project. So for this particular application, there's quite a bit of information to be entered in here. For our tutorial, I've previously populated that information. So let me open up the file. Again, here's where we could enter our project information. Under the comments section, I've indicated it's our utility source, which is two 2500 kVA transformers. I've just put that comment in. So now I've opened the file that was previously saved with all of the power system information and the load information. So the first item here is a utility transformer. If I select that utility transformer, actually this is the utility supply. So here we can enter it as a transformer if we know the utility transformer upstream. But in this case, we have short circuit information that the utility has provided us. So the short circuit current information is entered at 13.11 thousand amps, and the secondary voltage of the utility is at 13.8 kV. I could enter cable information if I had it. Often not easy to get. The cables will help a little bit in reduction of current harmonics, and therefore reducing the voltage harmonics upstream. But without the cables, the analysis is more conservative. So if we can pass without the cables, then we know we're going to pass if we add the cables to the system. So often, as I said, they're not available. We usually don't need to include them. And we have our user transformer. If I select the user transformer here, I've entered it as 5000 kVA. There are two transformers at 2500 kVA each transformer feeding one of the buses that shares the loading. So that can be represented as an equivalent circuit of a 5000 kVA transformer with the transformer impedance of 5.75%. We include the secondary voltage at 480 volts. There are efficiency information that can be included with the transformer that is useful for energy analysis. In this case, we're not doing the energy analysis, we're just doing the harmonic analysis, so I can just leave it as the default values. Again, we can put cables downstream. A conservative analysis doesn't use you don't need to use the cables for a conservative analysis. So now we get into our loading. The first branch for our load is our linear load component. I've entered 109 kilowatts, which is the equivalent of the 146 horsepower of fixed speed loads. I've selected 0.9 as a typical power factor for a fixed speed motor, and I've put in the comment field that these represent the fixed speed pumps. The first nonlinear load branch, and we have 9 nonlinear load branches we can enter. The first one is the air handling units that are equipped with EC fans, and these are the ones that have harmonic mitigation equipment included with them. So lineator harmonic filters included with those air handlers. There was a total of 600 horsepower of those. So if I click the circuit breaker here, left click on the circuit breaker, this is where I entered that data. So I can select the loading rating. So we've got 600 horsepower of total air handler fans. And we're going to simulate the worst case scenario. So that's at 100% loading. That's when our voltage distortion is going to be the highest. And these 600 horsepower are equipped with harmonic filters. We could have entered them if they weren't, just as a standard VFD, a 6-pulse VFD. We could enter them with our standard filter, which is just the lineator AUHF, but these are equipped with our high performance filter, the lineator HP, so I've selected that. We can enter AC line reactors or DC link chokes. The EC fans are equipped with internal DC link inductance. That's equivalent to 4%. So I've entered that information here. And then I can also show the smoothing capacitors. There are default values, but I've selected the smoothing capacitor for these EC fans. Then the next branch are the other air handling units that also have EC fans, but there's no harmonic mitigation. They were determined to be small enough that additional harmonic mitigation wasn't necessary. So those are going to be entered as 60 horsepower. They're actually 65 horsepower, so 60 horsepower at 107% loading will represent the 65 horsepower. They're going to be equivalent to a 6-pulse VFD. So we've selected that item. They have the internal DC bus inductance of 4%. So I'm selecting that. Then the miscellaneous fans. For the miscellaneous fans, there were 44.5 horsepower of miscellaneous fans. Again, I'm not able to enter that exactly 44.5, so I've selected the 40 horsepower. If I indicate loading of 111%, that will represent the 44.5 horsepower. There's 6-pulse VFDs with 5% DC bus inductance built in. So those are for our miscellaneous fans. Then we have cooling tower fans. The cooling tower fans, there were 4 15 horsepower cooling tower fans. I don't have an option for 45 horsepower, so I can enter it as 50 horsepower, loading at 90% to represent the 45 horsepower. The cooling tower fans also are equipped with DC bus inductance of 5%. Then we have the various water pump applications. The first ones entered in here are the standard water pumps. There were 95 horsepower of those, so I've entered them as 100 horsepower at 95% loading. They are 6-pulse VFDs, and they have 5% DC bus inductance. Then there's a group of AFI water pumps, chilled water pumps. There was 105 horsepower of those. So I've selected 100 horsepower at 105% loading. Now within SOLV, we don't have models for active front end equipment. There are too many differences in designs and too many different parameters associated with active front ends in order to model them accurately. So for this analysis, we're going to select the 18 pulse system, which for the low frequency harmonics simulates very closely to what an active front end VFD would generate on low frequency harmonics. So we select the 18 pulse system. That defaults to a 3% DC bus inductance. With that configuration, that closely models an AFI drive, excluding the high frequency harmonics, but that's extremely difficult to simulate, and that's something that has to be addressed separately. The manufacturers of those AFI drives are going to have to provide the information related to the high frequency harmonics if you need to do that analysis. So we'll enter those, and now we have the chillers, which are also active front end. We have 3 400 horsepower chillers, so we're entering those in at 1200 horsepower. With redundancy, those chillers will never be loaded more than 75%, so that's going to be their maximum loading. That's going to be our worst case scenario, so we'll enter that as 75% loading. We'll look at these as an 18 pulse system with an AC reactor and a DC link choke, because that more closely mimics or models the active front end chiller application. And the last nonlinear load branch are the other pumps on the system. Booster pumps, some medical equipment pumps. There's 100 on those other pumps. There was 107.5 horsepower total load, so I've entered that as 125 horsepower at 86% loading for a total of 107.5. And these pumps are equipped with 3% AC line reactors, so they're entered, that is entered in there as 3%. So now we have all of our loads entered. We can go over here and run our simulation. This is going to generate the results of the situation, so we can see at various points on the one line the information that's included here. We can print off this one line and include it in our report. We can also look at waveforms and spectrums at the various loading locations, and then we can click on those, and we can also include the detailed harmonics analysis on those. All of this can be printed, saved as PDFs, and entered into our harmonic simulation summary report. But well, our main objective was to demonstrate whether we're going to meet the harmonic limits of IEEE 519 2014. So as we can see at this point, at both the utility point of common coupling and at the secondary of the transformer, step-down transformer, we meet on both voltage and current harmonics the requirements of the IEEE 519 2014. So now if we want to look at a generator analysis when we have the loads supplied by a generator, I've created another file that I can open here, which is our generator information. And now we can see here we've got our generators. We have two 2000. Sorry, I selected the wrong side of that. We want to look at it from the generator side, so the lower. We have two 2000 kilowatt generators, and we enter those as a total of 4,000 kilowatts. Power factors at 0.8. and the subtransient reactance is 13%. So I can run the simulation here. All of our loading information has remained the same. We can go back into our IEEE 519 compliance report, and we see that with the generators, in this particular case with the harmonic mitigation that was included with the loads, we meet the requirements of IEEE 519 2014. Now when we have more complex one-lines where there might be a lot of downstream transformers supplying the loads. We might have a larger upstream transformer and then several loads downstream. We can enter branch transformers in each nonlinear load branch. We can enter an isolation transformer and an auto transformer. We can put phase shifting degrees. We can select the size of the transformer. SOLV will default to a particular size, but we can enter whatever size we want in here. We can enter the impedance of that transformer and then select that, and now we have a transformer branch. We can combine the nonlinear loads on that transformer, the similar ones, and do our simulation with these additional branches. So SOLV has the capability of modeling these very elaborate one-lines as well. So now that we've generated our simulations, let's look at how we might combine those into our harmonic analysis report. Now that we've completed the various simulations, they can be easily assembled into a concise and easy to follow report. Our recommendations on how to organize such a report are to include a list of comments and assumptions with the summary of the power system parameters for each source, the equipment list with loading assumptions, and a clear explanation of loads that have been combined on a particular load branch, explanation of loads that have been modeled as being similar to a model available in SOLV. For example, in this case, we modeled the AFI drives as 18 pulse VFDs. This may require an explanation as well of aspects that cannot be modeled or that weren't modeled, such as the introduction of high frequency harmonics that AFI drives can introduce. Then it's good to include an executive summary that lists the various simulations included in the report and highlights important simulation results, particularly with respect to the targeted limits as to whether they met those required limits or not. And then appendices for each simulation that was conducted. Thank you for sharing your time with me today. I hope you found this discussion to be helpful. If you haven't already done so, please look for other tutorials in our SOLV series to learn more about this powerful power simulation software tool. Thank you.